Guys ready? Okay. So our next speaker is Tom Talpe, and he's going to be talking about remote persistent memory. So you'll get a lot of good information from this. Over to Tom.
Thanks, Prakash. So hi, I'm Tom Talpe. I'm a developer and architect, actually, in the Windows Devices group under Mike and Henry Sanders. I am historically involved in the SMB3 protocol and in the RDMA protocols. RDMA, you may be familiar, Remote Direct Memory Access, is a very low latency, high bandwidth network technology. Runs over Ethernet, TCP/IP, and other protocols. And we've adapted SMB to RDMA with a protocol called SMB Direct. And so those have been my contributions over the years, and I'm still very active in that. I own the protocol documentation effort for the file sharing protocols, 40 odd protocols, mostly revolving around SMB. But a lot of others, the FRS protocols, a whole bunch of legacy protocols that we hope will slowly go away. You should come see Ned's talk tomorrow, or is it Wednesday? There's a lot to say about that. But anyway, you may have interacted with me in many different ways, even if you didn't know it. I own all those protocols. So the other half of what I do, though, is a storage architect for Windows remote file sharing, right? And that's sort of the behind-the-scenes ideas, development, trends, etc., and attempting to make new Windows features and new standards as well that Windows and other protocols, other implementations can use, right? Very similar to our strategy in Windows file sharing. And I've been very, very active over the past few years, mostly in the Storage Networking Industry Association, SNIA. I'm going to talk a little bit about the SNIA effort here just to kind of introduce it. And you can find a bunch of talks that I've given on this. And I've basically, I call it sort of a sliding window. I started with one set of concepts, and I've been sort of advancing the window into new areas that you may not have seen before, okay? I'll try to bring in some context from the earlier discussions, and I'll try to add some new context as I move this thing forward, okay? And I guess I also want to say that although I'm going to make some Windows product statements here, these are things that we've already shipped in Windows. I'm not trying to make any forward-looking Windows support statement here. I am not representing a Windows product commitment at this time. Other teams will make that commitment, not me. I'm basically charting the path, and so I'm here to kind of motivate you into the future, okay? Show us what we're thinking about behind the scenes, not necessarily what we're planning to ship, although I sure hope we're going to ship this stuff. So let's get started. The outline, I'm going to first sort of set the stage, just because I'm not sure that everybody here is in the Windows part of the agenda, so you may not be that familiar with persistent memory. So I just want to sort of talk a little bit about what is persistent memory and how does Windows support it. Along with Linux, actually, I'll mention Linux a few times. Second, what I'm looking at is the RDMA persistent memory extensions. In order to support persistent memory remotely, right, the first step is the local, right, which we have. To support it remotely, we may need some extensions, and I want to talk about what I've been doing there. And then to ground what that will mean, I want to talk about some example application scenarios. And you can, by the way, feel free to interrupt me. This is perfectly interactive if you want it to be. Okay, SNIA, Storage Networking Industry Association. I swiped these slides from a recent SNIA presentation. SNIA has been very, very active in the area of persistent memory, particularly with respect to the what's called the NVMP, the NVM programming twig. The P stands for programming. It's about an interface to non-volatile memory, which is kind of an old-fashioned word. I'll show how that's morphing over the years, but over the months and years. But SNIA has been really leading the way in persistent memory interfaces. The industry is building persistent memory devices, but how do the applications consume it? That's the answer SNIA's been looking to, or the question SNIA's been looking to answer. And these are really high-level basic things, but you can see that volatile and non-volatile technologies are converging. On the left is today, and actually the today is actually somewhere in here, in this space, more realistically. A conventional system today has DRAM and disk, and it has some memory and some storage. The storage or the memory is not persistent, however, and the storage is. As we move forward, this thing called PM, persistent memory, starts to sneak in, and it's in between the storage and memory area. Over time, it becomes faster and faster and becomes a pure memory technology. But it's persistent, so it has the characteristics of storage. It's really important. And some of these new and emerging technologies, probably the most important and visible one is this thing called 3D XPoint from Intel. It's also called Optane. That's their trade name for it, although Optane has been applied to the NVMe devices, the solid-state disk devices as well. But there are a bunch of technologies. There's also low-latency NAND, good old flash. There's MRAM, magnetic spin torque, all kinds of things. PCM, phase change memory, good old-fashioned PCM. The vision for persistent memory in SNIA's world and elsewhere is that persistent memory brings storage to memory slots. It's fast like memory, but it's persistent like storage, okay? And it's really real, but just think that it's memory and storage, and it will move more and more toward a storage paradigm. It's a type of non-volatile memory. There are two basic ways of exposing it. One is disk-like. You can think of it as a persistent RAM disk. It appears as a disk drive to the application. It's just a RAM disk, it's a hunk of memory that's exposed as a block device. It appears as a traditional array of blocks. It's usually software arbitrated. It could actually be a RAM disk driver, very often is. That's what it is in Windows, for instance, and in Linux. But it can also be an NVMe device. It can have the NVMe, NVM Express is sort of like a replacement for SATA, very high performance local interface to a disk-like device. The second way of exposing it, though, is the way you really want to, and make it memory-like, non-volatile memory. We call it PM, persistent memory at this point. It appears as memory to applications. It actually is memory in most cases. Applications store data directly into it. They do load and store instructions, CPU instructions. And there's no I/O, there's no DMA, there's no nothing. The CPU literally writes to it and reads from it as if it were memory. So this sort of two-personality nature is really important for application consumption of this new technology. So it's byte addressable. That's the key to persistent memory. The consumer's or the programmer's point of view is that it's byte addressable. I can read and write a single byte. In reality, it might be a cache line. It might be something slightly different depending on the hardware, but it's byte addressable. I can modify a byte, not like a sector of a disk. It's literally a byte in memory. Load and store access via CPU instructions. The device generally resides on the memory bus. Even if it doesn't reside on the memory bus, it's mapped like memory so that these instructions can execute on it this way. It has memory-like performance, in particular, ultra-low latency. It's the latency that really differentiates this thing. The latency is sub-microsecond, hundreds of nanoseconds, that kind of thing, sort of traditional memory latency. In particular, the CPU doesn't block waiting for it, right? You don't issue an I/O and then go do something else or go to sleep and get an interrupt and then you got your result. You literally read it and synchronously it returns that data. There might be a little bit of a stall, depending, but you don't block ever. It supports DMA, including RDMA. And interestingly, it's not prone to unexpected latencies. Tail latency is a real killer in enterprise workloads, right? And disk drives and NVMe devices, all kinds of these things, they have queues and the queues back up and they get tail latencies. And all of a sudden your 1 microsecond latency turns into these outliers of tens of microseconds. Those are really bad for enterprise workloads, especially when they happen on the critical operations. So this is very appealing in terms of predictable latency, low jitter. Terminology, just to wrap up this little bit of the introduction. There's a bunch of terms used to describe the hardware. Microsoft originally used to call it storage class memory, SCM, and a bunch of other people did too. That's kind of moving aside. Byte addressable storage was occasionally used. Everybody is converging on the term PM, persistent memory. Every once in a while, you'll see it as PMEM, just because people don't like to use just a two-letter acronym. But the idea is that if it's actual memory, it's going to be called persistent memory, right? Alternatively, the term non-volatile memory used to be used. You notice that the SNIA twig was called the non-volatile memory programming twig. But here it is developing byte addressable programming techniques. NVM became very confusing, like overnight. NVMe devices appeared, NVM over Fabric appeared, all kinds of NVM technologies appeared. They are different. In the NVM term is moving to describe block mode devices for the past few months. Intel's driving really hard on this terminology split because it's really confusing customers. NVM and NVMe, we as an industry have decided is a block device, right? Whereas PM is a byte device. And there's a block emulation for the byte device, that's fine. But it's NVM for block, PM for byte. Okay, second piece of background, Windows persistent memory support. This is what Windows does today. Persistent memory is supported in Windows 10 Anniversary Edition, what Mike mentioned earlier. That was back in the fall, August of 2016, as well as Windows Server 2016, which shipped in the October timeframe. Persistent memory support is foundational and SKU independent in Windows. It's supported in all Windows SKUs. If you look at your laptop, somewhere in that Windows System 32 directory, you'll find something called SCM bus and SCM disk. Storage class memory bus, storage class memory disk. I'll show you on a diagram in a sec. They're in there from Anniversary Update forward. If you drop a JEDEC-defined NVDIMM device into one of these two SKUs, it will see it by basically enumerating it in the BIOS. It will load the SCM driver and use it as an SCM device. It will be available to you as an SCM device. It's not ordinary memory. These things are slightly different from ordinary memory. They're a little bit slower. They behave a little differently. They require this commit, this flush operation to make things durable. So they are surfaced to the operating system and in turn to the application in specific ways. The access methods that application can use basically fall into three areas. The DAX file system. We used to have other names for this. We've basically unified the terminology with the Linux systems. DAX, DAX stands for direct access. It supports mapped files with a load store paradigm, right? Traditional Windows map files, map view of file, flush view of file. And the application loads and stores and then commits or flushes the data to the disk or to the backing device. In this case, persistent memory. Cached and non-cached both work with the read-write paradigm. You can, even though it's a mappable device, you can still read and write the files through the traditional API. And these two paths are actually consistent with one another. You have to follow the Win32 rules, and on Linux you have to follow the Linux rules. Caching works, everything works, but you have both the load store and the read-write paradigm available. I'll go a little more detail in a sec. The second access method is block mode, the so-called persistent RAM disk. It's a raw disk paradigm. That's that second driver I mentioned, SCM disk. SCM disk is the RAM disk for a PMEM device, right? And it's a slightly aware RAM disk. It basically behaves like an ordinary RAM disk, except that it understands it needs to flush data to the device in a special way. And so SCM disk arbitrates this block mode access. Block mode's really useful. You can create a file system on it, and it'll work just great. Might be slightly suboptimal, but it will work just fine. And applications like SQL Server can use the raw device if they are block mode persistent aware. And finally, there are direct application interfaces, mapped in traditional file, like I mentioned up at the top for DAX. There's this second interesting thing called the NVM programming library. That's available at a site called pmem.io. It's an open source library, largely championed by Intel, but it has half a dozen, maybe 8 libraries in it that support various flavors of persistent memory programming. It has a transactional library. It has low level and high level. In particular, the NVM programming library understands the quirks of the CPU and the platform, right? It understands that some CPUs have one instruction to commit and another might have a different one, and that some platforms might have different topologies and hardware under the hood. And it attempts to bring in all those things with a common interface for the application up top. So it's a convenience to the programmer. However, the programmer can also go to the bottom and just say, I'm PMEM aware, I'm on this platform, I know that CL flush opt is the instruction I want to use. I've checked that this won't fault on the Intel CPU that I'm running on, I'm going to do it myself. That's great, it works just great. So you can think of the NVM programming library as a programmer's convenience. In particular, it might be convenient for running on future platforms, right? As future platforms come along, the PMEM library will evolve, and the open-coded stuff, you'd have to do it yourself. So this is the Windows Direct Access architecture. It's a very similar architecture for Linux, I just want to mention. But up here at the top, you see a couple of applications. You see block mode style and a direct access style. And there are a couple of different ways that it can get to the SCM-aware file system. It can go directly via a standard file API. It can also open the raw volume and bypass all this stuff. Just go right down to the disk driver. But the standard file API will do reads and writes. It will do a setup through the SCM-aware file system, DAX, go through the disk driver, which is basically a null layer at this point, directly to PMEM. And so this is where we support the mapped file or the standard file direct I/O with read-write format. Alternatively, the direct access can memory map the file, and it does the setup path this way. But then this green line over on the right is what's really cool at that point, because once the file is mapped, it enters a memory mapped region, and loads and stores, CPU instructions, can go directly to the hardware. So that's pretty neat. The updates directly modify memory. These things totally bypass it. You can see they bypass the file system and the driver. You get the true device performance with byte addressability. The one thing that you lose is the possibility of filter drivers, which normally live up here above that file system, like an antivirus checker and stuff like that. But we have actually modified Windows Defender to nonetheless support NTFS, because it will still get the opens and the mapping calls, even though it doesn't get the reads and writes. So the antivirus driver is still in the loop for the important part of the operation. So I/O and DAX mode, memory mapped access is the one everybody wants. That's where you map it. It's true zero copy access to storage, right? You do a load and a store, the access goes directly to persistent memory. There are no paging reads and paging writes generated by Windows here, right? It'll either succeed or fault. However, there are the possibility of caching operations. Remember what I said about read and write being consistent with load and store. So the cache manager is still in the loop if you want him to be. When you open a file, you can open it in cache mode. And the cache manager can retain a copy. It's actually the actual contents of the file. No reason to create two pages with the same content. And it can copy directly between the user's buffer and persistent memory. So cached I/O can be used, read-write, with one copy access. In particular, it's coherent with memory mapped I/O because there's no copy of the cache, right? The cache is the data. But you have to remember that still no paging reads or paging writes are ever generated. Non-cached I/O, you'd think would be more difficult, but it's easy. We just make it cached. We just literally override the non-cached and make it cached. You've got only one copy of the data, so non-cached I/O is actually cached I/O. It's the same thing. So non-cached I/O is pretty cool, and non-cached I/O is also coherent, right? That's a surprise. Non-cached I/O is not usually coherent. So you get coherency for free. Backward app compatibility, the other way to get to it is a block mode volume. The SCM disk, RAM disk driver, right? It maintains all the existing storage semantics. All the I/O operations traverse the whole storage stack. Extra atomicity is guaranteed. So in a failure case, it either succeeds or fails the whole block. It has a shortened path length through the storage stack, so latency is reduced. I'll show you a little diagram. It basically works with everything, which is cool. So this was a performance comparison, and this was done about a year ago. I think this was done late summer last year, just before we shipped Windows 10 Anniversary. And we ran a trio of benchmarks. One on a best-in-class NVMe solid-state device. That would be a PCI Express device. We ran a 4K random write workload, one thread, single core, queue depth 1, right? This is the no parallelism, pure latency sensitive workload, right? Just how fast does it go without any queuing whatsoever? We're just going to do one operation, wait for it to complete, send our next operation, one after the other. So it's going to be very, very latency sensitive. We're going to get a true IOPS number. We got about 14,000 IOPS with a latency of about 66 microseconds through the existing stack, right? It went all the way down the storage stack. It issued an NVMe operation. It waited for the interrupt. It completed the operation. Okay, we got it 56 megabytes per second. We then ran that on a block mode NVDIMM. Same system, no change, just a different device. And we got about 10x the IOPS and 10x less latency. Everything went up by a factor of 10, right? And the only difference was, instead of doing an NVMe operation at the bottom of the stack, we were doing a data copy, right? We took the block, we went all the way down the IO stack. At the very bottom, we did a mem copy and returned. No interrupt, but also no IO. Finally, we did a DAX mode NVDIMM. We mapped it directly. Now the storage stack isn't even in the picture. It's all loads and stores. And those 4K writes turned into over 1 million IOPS. The latency plummeted to about 800 nanoseconds, and the throughput went up to 4.5 gigs. So this was a very compelling local result, right? Using DAX in Windows, just a little simple thing about how simple it is to do. On either of these OSs, you can do the traditional format command, this new flag called /DAX. Format volume, this is the PowerShell version of the same thing, is DAX $true, right? That's how you format a DAX volume. It's basically NTFS with a special flag. And there's the flag, file DAX volume. So the application can say, do I have a DAX volume or do I have a file on a DAX volume? You can do it with a fairly simple check. And this can be obviously wrapped up in a library, but you just inspect that DAX flag. So this is how you'd actually read and write it. The good one, the memory mapping version, you create a file mapping, you map the view, and you mem copy. And when you've dirtied all the pages and you want to commit them, you call flush view of file. That guarantees that it's safe. When flush view of file returns, you're guaranteed that the data has been made durable. You can also hand code it with non-temporal instructions. If you notice here, we did a mem copy followed by a flush. The non-temporal version, RTL copy mem non-temporal, bypasses the caches in the hardware, right? This is a special instruction in the Intel architecture. And so you no longer need the flush view of file when you're running locally. Now that's not 100% true remotely. I'll show you why. In the future, you don't have to hand code this stuff. You can just use the open source NVM programming language. Linux does the same thing. I just want to mention this. From 4.2, Linux has been supporting NVDIMMs. It became stable in 4.4. Currently, they're working on what, 4.11? Something like that. So it's been a while, that Linux has supported this as well. NVDIMM modules are discovered and presented as device links. You rarely open those devices, but normally you create a file system. And QEMU supports it experimentally. XFS and ext4 are capable of creating file systems on these devices. And a little bit about the stack, if you're really interested. The DAX for the file system extensions. BTT is interesting. The block translation table is how Linux lays out the devices. Basically, you access a logical block and it maps it to a physical block on the RAM. PMEM is the system physical address range where writes are guaranteed to be persistent. And the low-level programmable memory apertures. So these are just all some of the details of how Linux is implemented. All right, that's the background. How am I doing on time? Where's my timer? Oh, there it is. Okay. Remote access to persistent memory. So everything that went before was about local. It was about what the platforms are doing and about what the operating systems are doing locally, right? Which is really neat, but remote. One local copy of storage in the modern world isn't storage at all, right? You've got one copy. Well, big whoop. What if that machine dies? What if that machine is running in the cloud and I get migrated to some other place in the cloud? Oops, my data just, disappeared. You view one local copy as temp data, right? It's ephemeral. Could disappear at any time, literally, and probably does. Enterprise-grade storage requires at least replication. You need a multi-device quorum, right? You're going to write it to 3 places. If you're going to put it in an erasure coding in the cloud, you're going to write it to about a dozen places, right? You're going to smear it all over the place. And you won't call it safe until you've smeared it to enough places through the network. Well, that's important because that means that the latency of the replica is important. It means that I can't promise that the write is safe until I've replicated it, meaning that I have to go through the remote latency to do this, to make this guarantee. So, in addition, there are other semantics that we have. Integrity, right? How good is the data? What if it fails later? Privacy, do you encrypt it? How do you protect it? Manageability, can I rearrange it? Where do I know where it is? If I reboot, can I define it again? That kind of thing. All these are sort of part of the remote access problem. They're not part of the storage path necessarily, but often they are. But they are critical. So the value that persistent memory brings to this kind of environment is all about its latency, right? Today, we send something over a fairly high latency network that might be geographically replicated, for instance. And then we perform a write to a local block device that may have a queue and have unpredictable latency of its own, right? It might take hundreds of microseconds. It might take seconds, who knows? Persistent memory takes that last little bit and takes the latency and the jitter out of that picture. And so it becomes really, really compelling. Right? I can perform these writes in microseconds, maybe a few microseconds. I basically have a speed of light problem, right? I'm going to do a write. I want it to happen immediately when it arrives, and I want to know about it right away. So if I can get that down to a few microseconds, I have a totally new paradigm in storage, right? No more hundreds of microseconds. It's 2 to 3 orders of magnitude better than today's block storage, right? From hundreds of microseconds to hundreds of nanoseconds, can I get there? From seconds to single-digit microseconds, now we're talking, right? So, well, maybe not seconds, but in the cloud, that's possible. The obvious way to ride that path to the potential is to use RDMA. That's what we've proven with SMB Direct many times over. However, to do RDMA requires a protocol extension. That's where I've been working. In the RDMA protocols, we need a remote guarantee of durability. The way RDMA works today, an RDMA write, which is the direct data placement write operation for RDMA, there's also a read. But let's just focus on write for a minute. The completion of an RDMA write at the sender doesn't really tell you much of anything. It just tells you that the data was accepted to be placed remotely. It could mean that the local NIC has got a copy, and therefore, it's on its way. I promised you I'm going to make a good effort to put it where you asked. But the connection might break, the remote side might fail, all kinds of things could go wrong. You've received some indication that your write was successful. It's very much like a local write. When you do a local write, all you know is it's been accepted by the cache of the CPU that you wrote it to, right? and it will clunk down the way through the various levels of the hierarchy into memory sometime pretty soon. With a network, of course, you aren't sure because there's this thing called the network in the middle that might break. Your area of your error sphere is quite large. So RDMA write is nowhere near sufficient. So we early on determined that an extension was required. I and my former colleague published an internet draft for the ITF. We had a discussion in many standards organizations about this. I called it RDMA commit at the time. And it's basically like a flush view file, like a CL flush opt. It's an operation which takes any data which has been previously written and ensures that it's been pushed to durability. It does not return until that durability is assured, right? It may fail. Durability is not guaranteed. But once it returns, durability is assured and guaranteed. It executes like an RDMA read. If you don't know much about RDMA, don't worry about this. But it's basically ordered, flow controlled, and acknowledged. It's a well-behaved operation. Write is usually sort of a streaming operation. It's shoot and scoot, fire and forget. You push the write goes down the pipe, and eventually it pops out the other end of the pipe. But this would execute differently. It would go all the way to the end of the pipe, verify that it worked, and then come all the way back with an acknowledgement. When you received that acknowledgement, you knew you had durability. The initiator, in my view, requested specific byte ranges. It would say, I just wrote one page. I want you to clean that page. You might wind up having cleaned lots of other data, but all I want you to focus on and reply to me is that one page. There's been a bit of discussion about that as we move toward a standard. So I should put that in fuzzy text. There's, however, really strong consensus on the basics of, you do a bunch of writes, you do a commit. The commit returns when the writes are safe, made durable. The IBTA, the InfiniBand Trade Association, the SNIA, Storage Networking Industry Association, and the IETF, Internet Engineering Task Force, have all been discussing this. IETF, not so much. The one that I mentioned here, very much. The details are being worked out. The scope of durability, like I say, region-based, connection-based, are all under discussion. Connection scope is coming down as most efficient for implementations. Probably makes the most sense. And it says, everything I've written in this data stream, commit that. Don't commit everything on the system, that's all right. Don't commit just this tiny little bit that requires you to scoreboard it. But at least say that this stream of data, back to the last commit, has been made durable. But there are a few other things that might happen. Yeah, question, go ahead. So yeah, the question is, as I mentioned, executes like RDMA read. There's the pointer. Is that read or write? That's an actual read from the initiator. There's an RDMA operation called RDMA read, which basically says at this offset for this length, return the bytes that are present in the remote memory. You can do the same thing in the other polarity as an RDMA write. But an RDMA read is a little special in the RDMA protocol because it's acknowledged, whereas the RDMA write is not. So that's what I mean when I say executes like, that it goes through that two-trip or two-message exchange instead of a one-way exchange. So there are some RDMA-aware storage protocols, as a matter of fact. There's SMB3 with SMB Direct, and I've talked about push mode. This is an operation which would allow SMB3 to use this transfer model that I'm talking about. NFS RDMA also has it. I don't know if you know, but in my previous life, I was an author of NFS RDMA, the protocol. And we're just about to publish an update to that protocol, by the way, RFC 5666 BIS. That has a number, but I won't tell you what the new number is yet because it's still a secret. But there's a lot of work still going on in NFS RDMA. And the PNFS layout is very appealing for this. PNFS has the ability to sort of take a side channel, right? There's the NFS protocol for the metadata, and there's a side channel for the data called PNFS and a layout. And that layout could be an RDMA layout, which would allow push mode to work really, really interestingly. And there's a few other protocols. There are a few other RDMA-aware upper layer protocols, but these are the two. These file sharing protocols are the most logical ones that can adopt this type of model quickly. But I will mention that commit can work to any remotely mappable device. There's some wacky devices. There are these NVMe devices that have a PCI Express bar, a bus address register. They're literally mapped as memory, even though they're plugged into a PCI Express slot. They don't behave like memory in terms of speed, but they're accessed by the same API, quote unquote, as memory. Basically, anything that can be memory registered and accessed via RDMA could use this extension. And this is the example of push mode. I'm not going to dwell on it, but I'm just going to dump it out real quick. Like I say, I'm not trying to make a product statement here. This is a potential architecture. But we've talked about SMB3, RDMA, and push mode at previous SNIA developer conferences, last year, the year before, et cetera. And they basically do the same thing we saw in that DAX diagram, but they do it remotely. And so I drew the picture sort of left to right here. But basically, there's a DAX file system here and a PMEM array, right? So a DAX file lives in here. Normally, you would memory map it. Well, how do you memory map something remotely? You can't turn a write request on the client into an RDMA write request easily. But with the SMB3 protocol, we can actually have 3 different ways to access that memory. The first is the traditional way with an I/O request, standard old SMB3 read and write, possibly using RDMA, and we just do reads and writes to the file system, and we come down here. Remember, that gave us a 10x improvement in the first case. Second, we can do the direct mapped load and store from the SMB3 server. We can take a path by which, actually I should just advance, we can take a path by which the SMB3 server maps the file, puts it in the quote buffer cache unquote, and performs a direct file mapping access to the file. And third, and where it gets really interesting, is where we RDMA register that same thing. And we don't even use our SMB3, we use RDMA directly through the buffer cache right to the file. And so there are basically 3 paths. This skinny little one, the old-fashioned way, the load and store way that requires a changed SMB3 server, and the RDMA read-write way, which requires a changed RDMA protocol. Okay, so it's 3 phases. Great.
I just have a quick question. I was wondering how is the data necessarily laid out? Because so on the first one, which gives you like the 10 times improvement, you use the DAX file system, which in my mind suggests that the data laid out on the device is, I don't know, like a file system NTFS.
It is, exactly.
All right, and but when you do the load store direct to the device operation, how do you know where to get the data that you actually want?
That's what you get when you open the memory, the file, and you get a handle for the file.
Oh, okay,
so
there's open load store.
Yeah, exactly. Okay. Yeah, it opens it in DAX mode basically, and it receives a mapping from the file offset to the memory offset, right? So it has to sort of rearrange each load and store a little bit. But the file down here in PMEM is very unlikely to be contiguous. It's probably a list of pages scattered all over the device.
Exactly.
Right?
That's
so it has to go through that map to map the file offset to the memory offset to find the right byte. That's a pretty simple operation. So I think I talked about this path number 2. The path number 2 turns out to be problematic. It requires a good bit of interaction with the buffer cache, something we call CC in Windows, Cache Manager. And CC is not used to performing at this kind of rate, right? CC is a historical component of Windows that is now DAX aware, but is primarily sort of like, it just bypasses itself when it finds a DAX file. It just says, I'll manage your pages, but I'm not going to actually allocate a new page. This is your page, right? I'm just going to maintain the mapping. And it turns out there are a lot of funny overheads in there. There's a context switch in particular as you go back and forth between the server and CC. And so that kind of nibbled away at the performance benefit that we saw. We may or may not wind up implementing that just because of the performance goals. Sure.
Hi. How do you handle concurrent writes concurrency in this model?
How do you handle concurrency with this model?
Yes.
It's just the concurrency that you'd get from any other file sharing scenario, right? The upper layer would normally have to take a lease or an op lock of some kind to protect its access to the file if it was writing while others are reading, for instance. And that's what applications do with the Win32 API flowing over SMB. So we would envision that's what we'd call metadata in this case, right? That a number of different threads have access to the data. They're going to have to synchronize with one another to make sure they're getting a consistent view of it.
So the SMB protocol that basically will take the op log. So now it has connected to the remote, basically where the RDMA is happening.
Op lock is the old-fashioned way to do it. Yeah.
So
Leases are the modern way to do it.
Sure. So
Yeah.
does that mean that the op log also the remote has to be aware of the op log? So it's like
Sure. Yeah, absolutely. That's what it takes to be an SMB3 client. You have to be aware of the leases and the op locks. Leases are convenient because they basically delegate the ownership of the file, the lease, to the client, right? So the client can actually have multiple threads running there, and it doesn't even have to send the I/O at that point. It could completely cache the I/O because it owns that file or owns the state of the file at that time. An op lock is a little bit different, right? And there's some op locks that allow certain types of caching, but op locks are generally sort of recalled from the server, and they're kind of clunky. The lease is much more of a grant, if you will. You know, the client says, I'm going to open this file. There might be a number of threads who are going to open this file. I want permission to manage those. And so it manages the concurrency when a lease is in force.
Sure. Thank you.
So anyway, and either of these two modes, RDMA read, write, and load store, enable true zero-copy remote read-write to a DAX file. So they have that latency and overhead guarantee. This one may impose a little bit of latency. This one basically goes straight through the RDMA NIC. You're going to get exactly what the RDMA NIC gets to memory, right? But I just want to point out that even if we don't have all the RDMA extensions that I'm about to mention, we can still do these things by using the good old SMB3 protocol. And I talk about that in a lot more detail in the SNIA presentation if you're really interested in that. But there is a flush operation at the SMB3 level that can request that the SMB3 server perform that final durability step, even if we don't have an extension up here in the RDMA world. Which is great because you need a plan. You can't just say, the world will be great if you only adopt A, B, C, D, E, F, and G, right? Nobody will ever get there. But if you say the world will be better at A, better at B, better at C, better at D, better at E, and they all interoperate and they have a phased approach, now you've got a real story. And the interesting thing about these phases are that some of them are orders of magnitude. You know, I can say, you got 10x when you get to A. You got another 10x when you get to B. That's 100x. Okay, now we're talking, right? We're not talking about 1 or 2% here. All right, final phase of the talk here. Remote persistent memory workloads. And I really don't know where I am on time. What time is it right now? 10:47. Okay, great. I have till 11. At least I'm told I have till 11. Maybe I can just hog the floor if everybody's really excited. I'm excited. Okay, I'm going to walk through, I think, 4 workloads that we might use this type of device behind. And then I'm going to examine what we would need to do those remotely. Right? These are remote workloads, all of them. The first one, basic replication. Okay, I've written a copy of data. Maybe local, maybe remote, doesn't matter. But I'm going to write a bunch of other copies of the data to replicate it, right? I have to make that guarantee that I've reached some sort of quorum, that I've got a few copies in case one of them goes away. And I can be certain that your data is safe. So the workload is basically write, commit, write, commit, write, commit, write, commit. You know, I've performed a write, I'm going to perform another write and commit it, right? Maybe I do 3 or 4 of these things, but it doesn't matter. I might do more than one write, it doesn't really matter, but the point is that I'm literally just copying a write that I've already done and committing it every time I'm asked to do it, because I have to guarantee it's safe, right? So there's a few interesting things to look at. There's no overwrite going on here, right? I'm always writing a new block, right? I've written a chunk of data on this machine, on this node. I'm going to write the same chunk of data on another spot. I'm not overwriting part of the data. I'm literally replacing the data. Never overwrite. There's no ordering dependency, right? The only time an ordering comes into play is when I commit, is when I make my guarantee. Everything that leads up to that can happen in any order we please, right? It can be queued, it can go out whenever. Obviously, we want it to go out quickly, but we don't require it to go out in order. That's key. There are no completions at the data sink. The data sink, the place we're writing this to doesn't care that we're writing the data. All that matters is that we know the data is safe and we can go get it later. We don't have to tell the data sink that something has happened. So we really don't need much of a processor over there. We just need this thing to be a piece of memory on the network, network addressable, right? We probably use the CPU to set up the connection, but he's not in the critical path, so that his latency is not a question. He won't add to the jitter, for instance. He won't add to the overhead. And these things can typically be pipelined. Very often, depending on the way the workload works, there might be multiple commits outstanding. For instance, for multiple devices, right? You might have device A and device B both replicated to device C. So A and B are both doing write, commit, and they're pipelining and overlapping one another. Other semantics, asynchronous mode. We discussed this a lot in the SNIA non-volatile memory programming twig. We affectionately call it giddy up. And asynchronous mode is really important because normally, these write commits, you're sort of writing them, and then you're putting the commit right after, and you're waiting for the commit. But it may be that you're writing a lot of data before you commit, and you may have a lot of work to do. So the idea is you want these things to have a mode in which you can push them out asynchronously. You can say, well, here's a chunk of data. I'm going to write some more, but why don't you get started on this chunk? And that's really desirable for two reasons. First of all, it allows some pipelining and parallelism in both the network and the remote device. And second, it allows the implementation to be library-based, right? Normally, if you do a write locally, that doesn't trap to software. It's just a write to a chunk of memory, and the CPU executes it and returns, right? How does a library know that there's dirty data that can now be written? So by putting an explicit asynchronous hint in the interface, we can actually make the libraries more convenient. We can say, here's a 4K page, maybe you want to push it. It could be a no-op, doesn't matter, but we've informed the library that we dirtied a page. And so that giddy up is why we call it giddy up, Okay, we got a bag of grain on the back of the horse, giddy up, start taking it down the line. It enables that right behind, that's the key word. It complicates the error recovery, asynchronous mode, but in a well-defined way, right? If you get a failure, well, what data what data was bad? I had a big full pipeline of data, what's bad? But that's okay, we can define that. Right? We know that it's good up to the last commit. So what was clean then and not overwritten is still clean now. Reads are interesting too, but they're easily interleaved with the writes and commits. We don't anticipate any protocol implications for this workload except for the commit, the basic RDMA commit operation. Log writer. This is a slightly more interesting one. This is the first one, write a log record commit. That looks like the replica, right? Except now, once we've committed the log record, we're going to commit a log pointer, right? We're going to advance the pointer to say that record is good, right? We made it good, and now we're going to put it in the linked list, basically, right? We're going to advance the state with the pointer. And the pointer is usually a very small bit of data, It could literally be a pointer, a memory address. But it happens after that commit, right? After that commit, we write the pointer. If we wrote the pointer before the commit and the log record didn't get committed, that would be a very bad day, right? So right in between, right where that comma is, there's a little bubble in the pipeline where we have to block. We have to stop for a minute. The log pointer cannot be placed until the record is successfully made durable. You can think of it like a transaction model. So the implication is we must wait for that commit right, before performing that write, which is bad. We desire an ordering between the commit and the second write. And we've been discussing this for a couple months in the IBTA, and Mellanox and others have come up with a very simple and elegant solution. I had what I thought was a more elegant solution, but it turned out to be hard to implement in the NIC. So they have a simpler one. They call it a non-posted write. It's a write that behaves like a read. And by that, we mean that the low-level goop to implement the protocol makes it work like a read. It's queued at the sender, it does some processing, waits for that processing, and then returns. And so it's pretty simple. But the important thing that is ordered with respect to other non-posted operations. So for instance, it's ordered with respect to the prior commit, right? Normally the write isn't ordered with respect to anything. Writes are eligible as soon as they arrive, just like you were writing from the CPU. And this special non-posted write orders it with respect to that commit. And so it's a very elegant solution, and I have high confidence that the InfiniBand and Rocky industry love it. The iWarp industry is part of that same discussion, and they love it too, but slightly different protocol problem with iWarp. So everybody's moving toward this basic solution. Really great. The third is a log writer in the database environment. And our Microsoft SQL Server uses this in the Hekaton configuration. And there have been a bunch of talks on this, so I'm just going to remind people of them. But basically, there's a buffer that's held here in log buffers that are then queued into a full log record. And when the log record is full, it writes it to a log file. Traditionally, they would maintain the log buffers in some sort of high-speed device or memory, and they would sync it to some sort of IOP efficient device like a solid-state device, right? And they would basically buffer up, fill this buffer and drop it down as often as possible. And the problem was that these little red dots were where where the latency became critical, right? And so Hekaton moved these log buffers into an NVDIMN, into a local persistent memory array. And they still sync them out to an SSD, but by putting them in the log array, they sort of automatically get this behavior of persistence, right? There's no intermediate persistence phase. And they can still build up a whole log record, but they can do it safely. They don't have to wait for that whole log record to become full before returning. So basically, it allows a more rapid return here from number 2. And if you looked here, when they moved, this is called tail of log. This scenario is called tail of log. And you can see that they got approximately a 2x speed up at the transaction layer, which is pretty phenomenal. Now, what's interesting here is that there is an RDMA protocol implication here. And the problem is this is generally done with active-active signaling. In Hekaton, the idea is that you have two systems that are backing one another up, but they're active-active. They're both active database instances. And the other one can take over from the first one in case the first one fails, but they're two independent instances. So as one of them is replicating to the other one, it wants to notify the other one that data has been added to the queue. And so it will need to send a signal, an indication every once in a while when it's pushing data. The idea is to speed up that recovery. You want to reduce the time it takes for the remote node to recover from you, for you, if you fail, right? So that notification follows it. The important thing is that the notification has to happen here, right? After this operation has occurred, after the full log record has been built up. And so actually it can happen earlier too. But the idea is that as these writes occur, you need to notify. Remember in the previous thing, we didn't have to notify. All we had to do was write. And so there's a new discussion which may or may not succeed, but there would be an ordered operation rule for actually issuing a completion. This is a really tricky thing in the RDMA world because normally these read-like operations don't signal. They happen silently at the data sync. And so this is still under heavy discussion. I'm not sure this will, well, put it this way, I'm not sure that the complexity will merit the improvement. This may actually damage the RDMA protocol to go this far. So there may be a little bit of a pipeline bubble, which will add a little bit of latency to the signal, but that's okay. The data path is already way faster. And the final extension that we're only now beginning to discuss, but I've been talking about it for 3 years, and I as well put it on the continue to put it on the table, is data integrity. If we're doing all these writes, how do we know they're any good, right? Normally with a storage protocol, I perform the writes, and there's all kinds of upper layer encryption and integrity checks. And the remote server has processed this operation and has given me a pretty strong guarantee that the data is good and is safe. The RDMA NIC doesn't really give me that same semantic, right? It gave me a link layer semantic. It said, well, I checked some of the packet. I'm pretty sure the packet made it okay. And, I got a pretty good implementation, so I doubt I scrambled the data across the PCI bus. But trust me, in enterprise storage, you can't trust these statements. You absolutely cannot trust these statements. You must verify the data. And so who's going to verify the data? Well, so, we performed the write, we performed the commit. Now, who's going to tell me it's good? Well, the possibilities are kind of grim. Okay, I'll read it back. Well, there are terabytes of this stuff on a modern system. 3D XPoint today can put 6 terabytes on a server motherboard. 6 terabytes. I don't want to read back 6 terabytes, right? That would negate everything I just did, right? I could signal the upper layer. I could say, well, I just wrote this region, and I know I did it without telling you, but could you please go check and tell me if it's any good? And that's okay, but once again, we've gone back to that overhead that we were trying to avoid. We were trying not to signal that server. It's okay, we can do it, but it's there. And I want to point out that it might be the case that you want to build an appliance that doesn't really have such a CPU, right? Maybe it has a little embedded SoC device that manages connections, sets up the data path, and hands it over to the RDMA device. It may not be a very good choice for computing this thing. So I would love to see the NIC itself do this. The array scrub, storage management and recovery, right? I want to recover this data because one of my quorum members disappeared. So what can we do? The proposal is to add integrity hashes either to the commit operation or a new operation. I like it piggybacked on commit personally, but that's heavily dependent on the semantic. And the idea is that hash algorithms will be negotiated by the upper layer, but implemented in the NIC. And the NIC will be asked to check the hash. We have 2 options. One is that the client can send the hash to the NIC and say, is it good, yes or no? The other is the client can request the NIC to compute the hash and return the hash. There's a couple of pluses and minuses to those 2 semantics, right? In one case, it seems easier, right? Here's the hash, is it good or bad? But on the other hand, the other one might allow a different error recovery scenario or might allow different efficiencies. Right? The first one in particular, both ends know the hash is bad at the same time. In the other one, the data sync may never know the hash is bad unless the initiator tells it, by the way, that hash you gave me no good. The data is junk. So there's a little bit of discussion going on there. Interestingly, in the SNIA NVM programming twig, we have this option, this operation called optimized flush and verify, which is very much like a commit with an integrity check. We're talking about this. So the good news is that applications could use this immediately if they've implemented this API, which a lot of them have. And so to wrap up, 3 minutes over. Persistent memory is rapidly becoming part of the server hardware ecosystem. I didn't really talk about how companies are shipping this, but you can buy systems with NVDIMMs in them, with 3D XPoint in them today. And they are going to be more and more ubiquitous in server computing over time. I mean, literally by the end of the year, you're going to see them as a standard option for pretty much any server type device. Windows and Linux support is foundational and broadly supported. It's just out there. It's been out there for a year, maybe 2 years, and in our previews, right? you can count on the support for these operating systems for persistent memory going forward, period. It's there, right? In hardware and in operating systems. The protocol standards that I've been talking about there, those RDMA things, are well underway. We've been talking about them for about 2 years, talking about them seriously for just about a year, since last fall. It'll be a year by August. I'm really hopeful that we'll have some prototype protocol implementations at the RDMA layer this year, this calendar year. Really hopeful. We'll see. We'll see. It's not my job. I only work for Microsoft. We don't build a NIC, right? But the NIC vendors understand that this is a whole stack problem, and they're getting the message. I just want to say, watch for the coming revolution in low latency storage. It's really amazing. I mean, we're talking at least 2, maybe 3 orders of magnitude in latency improvement. It's going to radically change the way applications use storage. It's going to leave hard disks in the dust, by the way. They're going to be capacity, legacy, bit buckets. Save it. Spinning rust. Anyway. Yeah, more questions.
How do you expect this would work in a, say, storage system that has data efficiency, like compression and deduplication?
Sure.
This out-of-band data, writing data directly to persistent memory, how do you think this will play together?
Yeah, really interesting question, and does require a bit of a application refactoring, if you will, right? Normally, we perform things like dedupe at the server, right? We perform the writes, the server amalgamates the writes, looks at the local stored data, figures out how to dedupe it, performs the dedupe operation, right? And we can still do that. We can do that with this stuff on the back end, and we'll get the advantage of this low latency back end, but we'll still be doing the traditional network exchange, right, with a full-blown exchange with a dedupe filter in the middle. The alternative is to refactor it and move the dedupe to the initiator, right? And a lot of these things are actually, you can see this in many protocols from Microsoft. We're pulling the processing out of the server and into the initiator, right? We did this in the RSVD protocol, for instance, right? Where we put VHD processing on either side of the wire. It's your choice. You can do it on the server, you can do it on the client. And as you move it to the client, the management situation changes, the security, integrity, protection system changes. But it's certainly doable, and particularly with these modern high core count, high capability compute machines, it's quite feasible. So I view that as an ongoing discussion, and it is an important one.
Just one follow-up. There's any scope for extensions to the RDMA protocol itself to kind of enable this to be more streamlined in server implementations?
Yeah, are there extensions in the RDMA protocol itself that could take this further? Well, the answer is sure, but there are a couple of trade-offs to be considered. First of all, the RDMA protocol is basically layer 4. It's a network transport protocol. It has some additional semantics, so a lot of people sort of jokingly call it layer 4.5, but it is clearly, it's about carrying bytes across the network in an orderly, signaled, protected fashion, right? It is not about higher level semantics. So if you want to put storage semantics into the RDMA protocol, sure, but it probably won't resemble the RDMA protocols we see today. There are some RDMA devices that integrate upper layer behaviors. You see it in the iSCSI RDMA devices. You see it in the NVMe over Fabric devices, etc., right? But they have block semantics, right? RDMA doesn't really have block semantics. So, how much you push down into the device, I think, will be important. And then the second question is, how efficient will it be, right? Would you have been better off keeping it in the upper layer? There's this constant tug of war in RDMA. Well, the CPU can copy data really well. Why do I offload my data copy? Because it's so complicated. And, you tend to go through generations where you see these charts that show the CPU going up at one fairly smooth course. Then you see networks going up in a sort of a jaggy course. And when the network sticks above the CPU, everybody wants the network to do the work. When the CPU sticks above the network, everybody wants the CPU to do the work. And they tug a war, and every couple of years, one guy wins and the other guy loses. They go back and forth. Big whoop. But architecturally, I think you're talking about a valid question that I think a lot of companies will seize on the value of. But I think what's more important is to decide the storage tiers and the layers and where they're going to be implemented, right? We'd love to see them implemented in Windows, but that said, Windows wants to take advantage of these new devices that are coming down the road, right? We all want to take advantage of what we've got and do our best, et cetera. So we reevaluate these questions constantly. I don't think there's a single answer to your question, bottom line. But yeah, I would say, though, that I would be pessimistic that the RDMA industry can solve this problem. This is a storage problem, right? The storage industry needs to solve this problem. It needs to work with the RDMA industry to get the right solution. That's what I've been trying.
I think we're running about 10 minutes over right now, and I want to make sure we give Michiko time to talk before lunch. Thank you, Tom. That was a great talk.
Thanks.